Hi, everybody. My name is Ceren. So it's pronounced it Ceren. And I'm a current ITAMP fellow, hopefully starting my group next year. And I study, okay. I guess this is not going to work. I'll just use this. So I study quantum matter and then in and out of equilibrium from different perspectives. And today I'll focus particularly on many-body quantum chaos and quantum scars. And I'm going to differentiate quantum scars from quantum many-body scars. Okay. So let me first start with the chaos part. So the classical chaos that we're all familiar with is based on basis on the phase-space trajectories being sensitive to the perturbations, and this sensitivity is captured by the Lyapunov exponent. And quantum chaos is slightly different from that, but it still actually shares a common ground with the classical chaos. It was Wigner who realized that this sensitivity to perturbations in the classical physics can also be seen in quantum mechanics, but at the level of quantum eigenstates and the energy levels. So at the time, the people were studying the atomic nuclei, and they were trying to understand the energy levels. And the Wigner's way of looking at this was like, let's not look at them individually, but let's look at them as an ensemble, and let's study the statistical properties of the energy eigenlevels. And based on this, he argued that the random matrices could model the energy eigenlevels pretty good. According to random matrix theory, this is basically the theory of the random matrices, we expect to see a certain distribution coming out for the energy level spacings. And this distribution is called, in this particular case, Gaussian orthogonal ensemble. We also see in Ami's slides. So this is particularly the nearest neighbor energy spacing distributions. When you see this solid line, the Gaussian orthogonal distribution, one thing that gets our attention is that there is no probability at the spacing 0. So that means there is no two eigenenergies can be on top of each other, hence the name level repulsion. And coming back to this plot again, what you see behind the histogram is actually the first experimental data coming from an atomic nuclei level statistics. And this was basically the first evidence of the level statistics coming out. And then the second plot is actually, I think, much more interesting. They wanted to increase the data to average over, and they actually averaged over multiple different atomic species nuclei. And yet, even though these are different atomic species, we still see even a better way of this Gaussian orthogonal ensemble coming out. So it's basically a good evidence of the universality of random matrix theory. In fact, following on this, later Bohigas and Gianni Schmidt in 1984 put out this famous BGS conjecture. They studied a quantum billiard model, meaning a quantum particle subject to this billiard potential. And this model has a semi-classical limit, and they were able to see RMT, random matrix theory, coming out there as well in these nearest neighbor energy level spacings. And from there, they argued any quantum model with a semi-classical limit should actually follow these random matrix theory predictions. And hence, the level fluctuation laws are universal. So today, actually, this is basically one of the most well-known diagnostics of quantum chaos. Single particle or many-body, doesn't matter. And most of the many-body models don't have a semi-classical limit. So we still first go and check, basically, whether the RMT is satisfied or not. So, okay, this wasn't working. A recent experimental evidence of random matrix theory with the nearest neighbor level spacings came from Google team. And this was basically on a superconducting quantum processor. They were able to see the distribution coming out there as well. This nearest neighbor energy spacings capture the short-range correlations in the energy spectrum. But actually, random matrix theory has more predictions for for the energy levels. In fact, random matrix theory predicts longer range correlations in the energy spectrum as well. And this can be captured by what's called a spectrum form factor. It is defined based on a unitary, and these outer brackets are basically averaging over statistically similar systems. When we look at the spectrum form factor in time, we realize two features of it, a ramp and a plateau. In between, it connects at what's called Heisenberg time. Heisenberg time corresponds to the shortest energy level spacings. So basically, it is like the shortest energies that we can resolve. But then you can see this ramp behavior here. The ramp behavior, the fact that a system shows this ramp behavior in the spectrum form factor means that there are actually universal long-range correlations in this particular system. Okay, so recently I was giving a theory support for an experiment that was done in China in Ha Wang's group. And here, basically, they measured the spectrum form factor for two types of systems. One is periodically driven system, and the other one is time-independent Hamiltonian. Here, I'm just showing the time-periodic results. They have a superconducting transmon qubit quantum processor, and we were able to see, based on their the driving protocol, the ramp and the plateau behavior for 4 different system sizes. Of course, these are small because one of the biggest problems is that as you go to like larger system sizes, the coherence starts to affect your results, and you cannot really, in the raw data, you cannot really start differentiating ramp and the plateau because the system becomes non-unitary. We can see the orange markers are actually the raw data, and then if you do error correction, if you do error mitigation on this raw data, we can see the black dots here was able to capture that difference between ramp and plateau. So basically, seeing this ramp behavior in the data was the observation of spectral rigidity. Okay. So with the advance of these local random circuits, by local, what we mean is that a circuit that can capture the locality has like a linear light cone, like the model, for example, the brick wall model here. We were able to learn that there is actually more to many-body quantum chaos. Because so far I showed you a ramp and plateau, and single particle chaotic system will show ramp and plateau too. But is there any specific difference, basically, in the quantum many-body chaos that is many-body? There is indeed. So this new time scale called Talus time is actually onset of the random matrix theory. That means there is like an earlier time before the Talus time, which we call bump regime, because typically it shows this kind of behavior. And this was first seen with some techniques on the brick wall model and general random local circuits. And based on this, we took a few different cold atom models, more specifically the spinless and the spin-half Bose-Hubbard model, and we studied spectrum form factor on those. And what we find, regardless of the system that we have, and regardless of the symmetries of the systems, could be orthogonal or unitary ensemble, or the filling factor is the new here, we always saw this regime coming up. There's a Talus time and then a bump regime beforehand. And if we actually rescale the x-axis, the time with the Talus time, and the y-axis with the analytical prediction of the spectrum form factor, we see that the different system sizes actually collapse on each other, and for different parameters and etc. And in all of these, the scaling function turns out to be just a simple power law. So this basically suggested that we can write down a spectrum form factor with an early time correction as a power law. What this suggested, a universality in the bump regime. And in fact, there could be another universal regime to many-body quantum chaos, and capturing this longest range correlations. Because again, this is an earlier time than the Talus time. That is basically the longest range correlations that you can have in an energy spectrum. And this is beyond the predictions of the random matrix theory. There are still a few interesting questions here. For example, what could be the other observable effects of this bump regime? meaning the longest range correlations, especially in the quantum dynamics. Okay, so now I'm going to pivot, and I'm going to tell you about like one of the most important corrections to the ideal random eigenstates, which we've been talking about and suggested by the random matrix theory. And that one of the most important corrections is quantum scars. All right, so a quantum scar is a quantum eigenstate with an enhanced probability density around the periodic orbit. Okay? So a defining property of the quantum scars is that this periodic orbit has to be unstable and embedded in a chaotic region. Unstable periodic orbit means that when you calculate the Lyapunov exponent of this trajectory, it has to be non-zero. And physically what it means, if you start like moving on this trajectory, unstable periodic orbit, and if you're subject to a smallest perturbation, you will just go into this chaotic region. You will leave this periodic trajectory. And it was basically introduced to us by Rick Heller. Okay. So now we have this contemporary concept, quantum many-way scars. So the criteria for quantum many-way scars, let me repeat. So these are basically non-terminal, non-chaotic, low entropy many-way eigenstates that are embedded in an otherwise chaotic spectrum. An important property of them that they're negligible in a thermodynamic limit. Their numbers increase polynomially in an exponentially increasing Hilbert space. And depending on the model, for example, this particular one here, these black ones, right? So they could be spaced from each other in equal energy distances. They were first found, as Misha told us about, in the Rydberg atom array experiment. And that's partially because these are very low entangled eigenstates. And in a lab, typically what's prepared as an initial state is a low entangled state. Hence, when you start from these product states, which is a nail state in their particular case, you go and like overlap with them. And this gives rise to these anomalous, kind of remarkable oscillations in a system where we expect thermalization. Okay. So, well, we can ask, quantum many-way scars, but what's exactly scarring in a quantum many-way scar? Because when we say a quantum scar, like there's a clear visual that a quantum eigenstate has to be scarred by a periodic orbit. So if you want to talk about like scarring in the quantum many-way scars, we need to make a connection to the periodic orbits. And this is very hard because quantum many-way systems, as I said before, typically like a semi-classical limit. That means you have to actually come up with some effective phase space, probably just describing a corner of the Hilbert space, okay? And this is what these very interesting works did. They worked on the Rydberg atom array model, and they basically wrote down some effective phase spaces based on a matrix product, say ansatz. And as a result of these works, to date, basically there is no quantum many-way scar originating from an unstable periodic orbit embedded in a chaotic phase space. So instead, actually, quantum many-way scars seem to be associated with regular regions, okay, in these effective phase spaces. So I'd like to pause here and ask whether there's any questions about this part. Okay. So the reason why I'm saying that is because yesterday you saw this in Misha's slides as well. But this effective space is actually two-dimensional. So in two-dimension, you cannot have chaos. It is a regular region. It's an unstable periodic orbit living in basically a regular region. And later, actually, Maxim's work generalized this effective space to higher than 2 dimensions, so 3 or 4, so that they could actually have mixed phase space. In this particular case, they found quantum many-way scars are actually associated with the regular regions in the larger and generalized effective phase space. So we want to bring a fresh perspective to this problem by studying a rather unusual model of a spinor condensate. It's unusual in the sense that because in quantum many-way scar business, people study locally connected systems. And this model that we're studying here is a spin-1 gas. And that means there are collective interactions. But an advantage of the model is that there is a semi-classical limit. So that means we can go to the phase space, study phase space, and hopefully find an unstable periodic orbit embedded in a chaotic region. And that can give us a quantum scar. I won't get into too much details how we drive this, but we start with a spin-1 spinor condensate and work in the single mode approximation limit, which basically takes out the spatial part out of the Hamiltonian and gives us basically a spin model. It's a spin-1, so 0, 1, minus here basically are the levels of the spin-1 object. This Hamiltonian is actually studied a lot in the literature. It's very famous in the community of spinor condensates, but it's an integrable model. And we want chaos, so we're going to break the integrability. And I won't show all these details. In the end, what we end up with is this simple Hamiltonian here. The green part is the interactions, okay? Density interactions. And then the red part is the integrability breaking term, which is the mode mixing term. So at this point, we focus on the spectral properties of the eigenstates right in the middle of the spectrum where there is a diverging density of states. And here we find two types of states. The most of the states are saturating the largest entanglement that we can have in this system. And these states are also showing level repulsion, so they are chaotic, they're thermal. And if you look at the observable dynamics, we see the observables thermalize. Hence, we call these ergodic band of states. On the other hand, there are these other regular-looking states. Their numbers are much lower than compared to these ones. But their properties are also pretty different. So they're low in entropy. They show level bunching. That means they're not chaotic. They don't actually thermalize. In fact, if we initiate the dynamics on these states, we see this robust oscillations in the observable dynamics with very large fidelity of the time-evolved state with respect to the initial state. I won't get into details, but we also find that these states actually originate from integrability, and they have an approximate spectrum generating algebra. So I can explain if you ask me what that is, but what's important here is that all these properties are also the properties of the quantum many-body scars. Okay? So this is when people want to go and look for quantum many-body scars, these are the properties that they try to check. But we call them regular states because there is one important difference. Regular states here, as we call them, increase polynomially in a polynomially increasing Hilbert space. Okay? So that means they're not negligible in a thermodynamic limit. Okay. So I told you that one strength of this model is the fact that there is a semi-classical limit. So we can go and study the phase space. This can be done by writing down the state in the coherent state basis and solving the equations of motions that we derived. In the end, what we end up having is a four-dimensional phase space. And we look at the Poincare sections in this four-dimensional phase space to be able to visualize this phase space. And we find a mixed phase space. So that means most of the phase space is chaotic, which you can see with the Lyapunov exponents here, where there is a family of unstable periodic orbits embedded in this chaotic phase space. And then there is this regular region, which are composed of the stable periodic orbits. Okay, and now we want to see what these periodic orbits correspond to in the quantum eigenstates. To do that, we fix the energy density, and we first take a state from the regular region and calculate the Husimi distribution for this. That means the overlap of these quantum eigenstate with the coherent state basis. And this gives us basically such a phase space picture that is corresponding to these stable periodic, stable orbits basically. So take home message from here: regular states follow stable periodic orbits, hence the name regular, but they have the same spectral properties with the quantum many-body scars. But we had also this unstable periodic orbit. So what does that do? For this, we take a state from the chaotic region, very counterintuitively, and we find these states actually do show scarring. So these are actually quantum scars. So from here, I like to say that regular states and quantum scar states are pretty different from each other. Okay? So regular states are low in entropy. They don't thermalize. They don't show chaos. Almost perfect fidelity and oscillatory observable dynamics for long times, but they are also associated with stable periodic orbits in the phase space. In contrast, we find quantum scarce states in this high entropy region, which basically doesn't necessarily prevent thermalization, and in our particular case, they don't. They show chaotic behaviors, and even though there is some early oscillatory behavior in the observables, eventually the observables thermalize. So the take-home message is the spectral properties of UPO scarred eigenstates are very different from the properties of the quantum many-body scars. Okay, I'd like to pause here and ask whether there's any questions. Yes?
What's the definition of entropy for common state?
Yeah, so here we are using particle entropy because this is a gas, right? There is no spatial structure to it. You can basically work with different kind of entanglement entropy measures here, and the one that's suitable is a particle entanglement entropy. Right, so I'd like to show one more thing, given that I have, I think, 5 minutes. Okay. So this model that I showed you, because I took out the spatial part under single mode approximation, mapped us to a few particle model, right? So I like to actually work with a many-body model now. And in order to do that, we took this model and decreased the range of interactions. And we went all the way to the other side, which is basically a nearest neighbor, a chain of a chain of spin 1 atoms, or spin 1 chain. So we actually go through exactly the same. We write down the Hamiltonian exactly in the same way that we wrote down for the gas, and go through the steps, which I'm not going to talk about. But in the end, what we end up having here is a model that is a quantum many-body model. Of course, it doesn't have a semi-classical limit because it's a many-body model, but at least it has a mean field limit. And that mean field limit, we know it very well. We studied the phase space very well. There is a family of unstable periodic orbits living in the chaotic phase spaces. So this is basically our best chance if we want to find the signature of those unstable periodic orbits, having any kind of signature on the many-body states. So we basically start with this, it's type of Heisenberg interactions, but then there is like a field here. We start with a relatively high field. We study this limit because, again, we know in this particular case the phase space is fully chaotic with some unstable periodic orbits in it. And we find that we find volume law entangled states throughout the spectrum. We found thermalization is satisfied, but very interestingly, when we look at the projection to the mean field manifold, we see basically a scarring in the Husimi distributions of these many-body states. Okay, so there is like a comment. I need to make a comment here. You can ask like how come like we can see this kind of behavior, because what we expect from a random eigenstate is like no structure at all. Okay. In their Husimi distribution. It's like volume line entangled, it's thermalizing, it's thermal, it's chaotic. So according to like random matrix theory, according to various random wave conjecture, we shouldn't be seeing this kind of behavior. This can be explained by asking the question, how much of the quantum many-body state is contributed by the mean field manifold? And in fact, it turns out to be not large, okay? So it's small amount. And that is the reason mainly why we see thermalization. But again, I like to reiterate, we are just trying to see whether there could be any kind of signature of these unstable periodic orbits living in the chaotic phase spaces. And it turns out actually, in the dynamics, we can see this. In the early time dynamics, we do see some oscillations exactly with the unstable periodic orbit frequencies before the thermalization happens. If we start the dynamics on a coherent state on the unstable periodic orbit. Instead, if we start the dynamics on a coherent state, with a coherent state not on the UPO, but in chaotic phase space, then we don't see those kind of oscillations, okay? And it's easy to understand why this must be happening. If we look at the overlap of these initial eigenstates that I was talking about with the eigenbases. So if you look at that overlap for the initial state on the U-pole, we see these well-resolved kind of towers of states that are separated from each other with the U-pole frequency energy. Okay. But if we actually look at the same quantity for the chaotic state, we don't see such a structure. So then it's clear, basically, these early time oscillations are caused by these like towers of states. So the take-home message is quantum dynamics follow these unstable periodic orbits hidden in the classical chaotic phase space. But of course, it's not the entire story, and that's why there is a thermalization. So we call these thermal quantum many-body scars. I'd like to just wrap up very quickly by saying that there is one little bit of left in the story, which is basically the leakage. So if this red chunk here is our phase space, we can talk about two diagnoses for instabilities. One is the classical instability, which is captured by the Lyapunov exponent for the entire phase space. But then there is also this other instability, quantum instability, or leakage, also called in the literature, that is the rate of quantum many-body state escaping or leaking out of these mean field manifold or the effective phase space into the rest of the Hilbert space. Okay, that's what's shown. And what we see for our model is that we see relatively large leakage, and that explains the thermalization again. So from here, I like to quickly wrap up. I like to say that we aim to have a unified framework of quantum scarring phenomena that can encompass both the traditional definition of quantum scars as was defined by Rick Heller, but also the contemporary definition of quantum scars, the quantum many-body scars, as talked in the literature. And for this, we need to take into account both the classical and the quantum instability measures, basically Lyapunov exponent and the leakage. And I already talked about some of these regimes here with you. I didn't mention this, the non-thermal quantum many-body scar one, which we call non-thermal, but this is the quantum many-body scars that you would come across in the literature. You can ask me the details if you want later. I just like to mention a very interesting outlook idea. So based on these, imagined classification or framework regime, we can also ask the question whether we can have a classically unstable region, which can have a U-pole in a chaotic phase space, basically, but covered in a quantum stable region. So basically having small leakage, but then large Lyapunov exponent. We don't know any example of this, and we can even ask whether it is actually possible to have such a regime, like fundamentally, whether it will be possible to have. I think this is a very interesting prospect for this work, for the future. And I'd like to thank you for your attention. Happy to take questions if there are any.
Okay, thanks a lot for this very nice talk and also covering the whole history of ITAMP from the early. So the first questions.
I had one little question and maybe one broader one. There was a few slides back you had when I initialize in some state and then watch dynamics, it either oscillates or doesn't.
Uh-huh.
But it looked like you were initializing in an eigenstate, so why is there any dynamics? I just didn't understand.
Oh, no, we don't start in an eigenstate. We initialize in a coherent state, which is typically a superposition of many eigenstates.
Okay, so the psi sub n was not an eigenstate, nth eigenstate. I think that's what was
No,
on the figure.
that is basically what we are measuring is the observable. You talk about this one, right? At 0?
No, it was earlier.
Earlier. Okay, I think this one.
Yeah,
Here?
A. It says psi sub n and not psi n.
Yes. So yeah, this is basically the population of atoms, population of the atoms with in the 0 spin sector, because it's a spin 1 object.
No, but okay. Psi n. What does psi n mean?
Oh, that is basically the eigenstate expectation values.
But eigenstates don't evolve.
Yeah, no, actually, this is just confusing here. No, yeah, you shouldn't be looking at this, right? So
Okay.
what this is actually you start your initial states like either in a coherent state or in a Fock state. Definitely, like they're not eigenstates.
Right.
Yeah.
So, and the other question, I guess, is there anything particularly quantum about the last things you were saying? I mean, like if I have a classical many spin system, totally classical dynamics, and I think that it has some effective, simple mean field dynamics that's sort of correlated across the system, but not exactly. Like say it was integrable as a chain.
Okay.
But then I broke that a little bit. I started in some trajectory that I know is going to oscillate for a while, but it'll leak out. And so I write down a dynamics, it ignores the fact it leaks out, and then it leaks out. And eventually isn't that thermalization just in classical systems too?
I guess, so that leakage itself, I think, brings some quantumness there because I write down a mean field manifold. Indeed, if everything's staying there, then it is like really classical. I would agree with that. But if it's like leaving, if a quantum state, many-body state is leaving out of these mean field manifold, which is like captured by this like leakage, then I do actually expect that quantum many-body state to get more and more entangled. And that's like, can be taken as a definition of quantum state because there will be entanglement in it. The thermalization that happens there is like a quantum thermalization. It's like explained by the eigenstate thermalization hypothesis.
I mean, that's all much later time. I mean, this is you're talking about oscillations that go for a little bit and die. It has nothing to do with eigenstates at the end, at Heisenberg times.
Which one are you talking about especially? Like, I was talking about this one. Let's see. Right.
Yeah.
So
So you have three oscillations. I don't imagine it has much to do with the eigenstates at late times.
The thermalization happening here is what can be captured by the eigenstate thermalization hypothesis. It's a closed, isolated quantum many-body system.
Yeah.
So it happens because the state actually at that point is pretty entangled. Yeah.
Okay, sure.
Thank you.
Question: would a quantum state held by a chaotic pond, let's say we have a small chaotic pond and a quantum state that does not leak from it, would that answer the last proposal? Would that fit it's classically unstable and dynamically just a quantum state that would not leak outside?
Just one point, like what do you mean by one point?
No, pond. Think of a small region which is chaotic, the opposite from the island, okay? So it's the
Yeah, I think that
would,
sounds like a
so we
very
should
very
talk.
nice
Okay.
picture for it. Yes, I think that is pretty much
So there
what
is
I
such
am
an
imagining.
Okay.
Maybe we can chat. Yeah.
Okay, any one urgent question.
No, it's not urgent. It's instead of educating myself, I ask you. Actually, in a model which has no semi-classical limit, if I add random measurements, does it then become? Would it then have a semi-classical limit?
Well, so if I add measurements, it's possible that I might have some sort of transition to the area law states, because with the measurements, eventually with the probability of those measurements, you can actually have such a transitions, volume law to area law. And if you have an area law, it might be possible. I mean, I think that depends on what kind of model that we have in the end. I have to think about it more carefully before saying anything about this. Yeah.
Okay, so with this, let's continue further discussions over the coffee break, and let's thank Ceren again for this very nice talk.